Hello, happy Monday, 7th grade. We are moving away from just solving equations. Students had their concept test on looking at balances and solving equations on Friday. And now the purpose of using these solution strategies is how can we solve statements that are inequality statements. So when you've got an equation, there's only one number often that's going to make that statement true. When you have an inequality, often there's an infinite number. Anything that is going to make it less than or greater than would work. And how can we describe the entire solution set that's going to work for all of them? So we started by, well, let me just do a quick rundown. This was on the homework over the weekend and on the homework quiz, so kind of before we get to the blueprint, a rundown of what some of the different terminology means. So if I had x is greater than 2, I know some things about what this should look like just based on the statement that I see. X is greater than, which means it can never be 2. X can never equal 2. And anything for x that's greater than 2 is going to work. So if I wanted to set up my number line, I know that 2 is going to be kind of my balance point, but I'm not going to fill it in because x can't be 2 itself. So then if I were to kind of keep filling in the number line, I want to describe every number that's going to satisfy this. So every number that's going to be greater than 2. I know that 3 and 4 both are greater than 2, so I would then shade in everything to the right of that point. So all of those are going to work. If instead of greater than, I had greater than or equal to 2, that means now that x can be 2. That works. So I could fill in 2 as a solution. And then if, on the other hand, I had x is less than 2, it's going to look a lot like our first one, just flipped, because anything that is less than 2 is going to make this a true statement. And if it was x is less than or equal to 2, it's now going to look like this, but with the 2 shaded in because 2 is a possible solution. So that's the notation that we're going to be needing to use, and students should be comfortable using those in their mathematical discussions. So we've got a problem which is in the blueprint if you want to look at it more carefully, and it talks about my snack eating habit at school. So, you probably know that Miss Carter relies on snack food for her meals at school. But what if she decided only to eat goldfish for an entire day? The packs of goldfish each contain 200 calories. If that's all she eats, how many packages could she eat while respecting a 1,500 calorie per day nutrition recommendation? So things that we know. I know I cannot go over 1,500 calories. So if I can't go over it, then that means it needs to be, whatever happens over here needs to be less than that, or it could be equal to it, because it can't go over 1,500 calories. Now I know that one pack of goldfish is going to have 200 calories. And so I want to think, well, what could I do if I wanted to get up to 1,500? I could multiply it by however many packs I think I'm going to be able to have. And this would be an inequality statement that I could use. So we had some students who came up with inequalities like this to describe the situation. And I'm going to hold on to that and bring it back out later. And we had some other students that thought about, well, what's the maximum that I could have? If I can have 1,500, they used some equation solving strategies and divided both by 200 to say, well, then I could have, the number of packs could be 7.5. And that's going to get me to 1,500 exactly. I had some other students who worked up to it. They said, well, if I had one pack, that would be 200 calories. If I had, let's say, 5 packs, that would be 1,000 calories. If I have 7 packs, it's going to be 1,400, and if I had 8, it's going to be 1,600, and that's going to go over, so that doesn't work. All of these work, and that doesn't. So this was a nice way of looking at some possible solutions, and then where you definitely don't have a solution anymore. Over here, though, you get the exact point, because 7 doesn't work. 7 works, 8 doesn't. 7.5 does work. So that's going to be our balance point where we have exactly 1,500 calories. So if we were to look at this again, we could say that if P equals 7.5, then we would have exactly 1,500 calories, and that would work. But all of those other ones that people were listing would also work. You could have 1 pack, 2 packs, 3 packs, 4 packs, 5 packs, 6 packs, 7 packs, and all of those are going to be under, and that's where you get in the less than part. So if I wanted to graph that, we're not talking about a negative number of packs because that doesn't make sense. I can't eat less than none. So I'll think about everything between 0 and 8. And if we said that this was 7, maybe we would say then that this would be 7.5. That would work all the way down to 0 packs. And anything in here could be the number of packs that I could eat. All of those would work. Okay. So we're going to use this idea of a balance point, that place where you exactly equal something, to talk about how you could use an equation to help you solve an inequality. I showed students 5 different statements. They all had the same thing on the left and the right side, but they all had a different symbol. So it ended up being a different statement because of that. So the first one that I had was 2x plus 5 equals 13. Most people looked at that and they had something fairly quickly. Either they used a number trick, or they used a balance, or they looked at it and they said, I already know, I can see what x would have to be for this to be true. And whatever method they ended up using, they said x would have to be 4. Because if you did 2 times 4 plus 5, you would have 13, which is equal to 13. So x plus 4 would be the one solution to this equation. How can we use that, though, to talk about the inequalities? So the first one that I gave them was 2x plus 5 is greater than 13. People ended up telling me that this would mean that if 4 was our balance point, we would need x to be greater than 4 in order for this to be true. And they ended up marking that if you had 4, 5, 3, 4, 5 on there, they put an open circle and then went to the right. The way that we could check that that's actually true would be to try 3 and try 5. So let's do that. So if I tried 3, I would end up with 2 times 3 plus 5, which would be 11. 11 is less than 13, so 3 does not work. If I tried 2 times 5 plus 5, I would have 15. 15 is greater than 13, so 15 does work. 5 is in my solution set, so all of these are possible solutions, so that one would be good. On the other hand, if I wanted 2x plus 5 to be less than 13, well, we've basically done the work with those the trying 3 and trying 5. We know, so 2x plus 5 is less than 13. We're saying we think x would have to be less than 4, just the opposite. So if you had 4, you had 3, you had 5. We already tried. 3 is going to give you 11. So if you try x equals 3, you would end up with 11, which is less than 13. So your graph of your solution set would have to go to the left. Only thing that's different when you have that greater than or equal sign is that now it could actually be equal. So now if we said 2x plus 5 is greater than or equal to 13, that's added only one solution. X could be greater than or equal to 4. So all that changes is that 4 is now a solution. If we said that 2x plus 5 could be less than or equal to 13, we've only added one solution. X could be less than or equal to 4, so we could have 4 as a solution, so we would fill 4 in. So basically on your graph, anything that's colored in or shaded, that is a solution. That would make your statement true. But I keep talking about solutions, and I just wanted to get a very clear sense of what I'm talking about when I'm talking about solutions. So students had 3 notes. First one was, what does the word solution mean? And it ended up not just being an answer. A lot of people were saying intuitively, oh, it's the answer to the problem. But it's not just that. It is whatever makes a statement true. So it would be any number. Could be more than one number. If you're talking about inequalities, you have a lot of numbers that could be true. Any number that makes an equation or an inequality true. For example, if we have the statement x is greater than 3, 5 is a solution because 5 is greater than 3. 6 is a solution because 6 is greater than 3. 3 would not be a solution because 3 is not greater than 3. 0 is not a solution because 0 is not greater than 3. So we're looking for those things that do make an equation or an inequality true. Next, when I'm talking about a balance point, this is me using the language that we've already been developing with our equation work. The balance point is going to be the place where you have balance. So it means you need to be equal on both sides. So it is whatever makes your statement equal. For example, if we had 2x plus 5 is less than 13, x equals 4, that is the balance point, because that's the place where you would have 13 equals 13. I'm not saying that x equals 4 is a solution. I'm saying that that is the place where you would have the things on both sides equal. So then to check if something is a solution, plug it in. Like we did for 3, I think we did for 3 and 5 when we had x equals 4 as a balance point. Just to kind of reiterate and remind you of that, if we had 2x plus 5 is less than or equal to 13, and I knew that my balance point was 4, and we're just trying to decide, is it less than 4 or greater than 4? I'm going to pick one number that's less than 4 and one number that's greater than 4. Let's do 0 and 10 this time since we already did 3 and 5. So we'll try 0 and we'll try 10. If I do 0, 2 times 0 plus 5, that's 5. 5 is less than 13. So that fits our statement. That works. If I do 10, 2 times 10 plus 5 is going to be 25. 25 is actually greater than 13, so that would not fit our statement. It would not work. That tells me that, well, we've got 0. 0 is less than 4. X has to be less than 4. And so then I would have on here 4, 0, and I know that I need to go in the direction of 0 because those are both solutions. So that's one way that you can check to make sure that you've got a solution set that's going in the right direction when you've got an inequality. So we had 2, and I'm just going to go through one of them because soon I will have to pay if I go over 15 minutes. So we're just going to look at 1. 3x plus 2 is less than 17. So I'm going to start by finding the balance point because that's going to be the limit. I could use the algebraic method here. 3x is less than 15, so x has to be less than 5. So 5 is my balance point, and I now want to confirm that it's actually less than. So I'm going to try, since it's 5, I'm going to try 4, and I'm going to try 6. So 3 times 4 plus 2 would be 12, plus 2 is 14. 14 is less than 17, so 4 works. 3 times 6 plus 2 would be 18, plus 2 would be 20. 20 is greater than 17, needs to be less than 17, so 6 does not work. So 4 is less than 5. That definitely works. And that means that then 5 would be my balance point, but 5 is not a solution. So I would leave that open, and then I would want to go in the direction of 4. So I would go everywhere left that is less than 5, and that's what I would have. So use what you already know about solving equations, and now kind of take with that this idea of what is going to make a statement true, and test it. Don't just assume, oh, I think that the sign's going to stay how it looked like it stayed at the beginning. because we're going to see tomorrow that things are going to get a little more complicated. Have a good night.